Imagine a 100,000-ton ship drifting in the middle of the ocean, pushed relentlessly by wind and waves, vulnerable and alone. Picture this massive vessel, a floating city of steel and machinery, seemingly at the mercy of nature's raw power. You'd think its anchor, that giant hook of steel waiting at the bow, is what keeps it steady. After all, we've relied on anchors for thousands of years. Ancient mariners knew that dropping something heavy into the ocean would stop their ships from drifting into danger. It seems straightforward, almost primitive in its simplicity. But here's the truth that most people don't realize. The anchor itself doesn't hold the ship. Not really. The anchor is only the beginning of a much smarter system, one built on principles of gravity, geometry, and friction that work together in ways that seem almost counterintuitive. Think about it this way. A modern anchor can hold a ship 1,000 times heavier than itself. Yes, you read that right. A single anchor weighing perhaps 15 tons can prevent a 100,000-ton vessel from moving. That's not because the anchor is miraculously heavy or some feat of raw strength. No, it's far more elegant than that. It works because of how the anchor digs into the seabed, how it penetrates and grips the sand or mud below, and critically, how the chain behaves beneath the waves. The chain is where the real magic happens. When an anchor is deployed, it doesn't just hang vertically like a rope. Instead, it snakes across the ocean floor in a long, nearly horizontal line. This is called scope, the ratio of chain length to water depth. A typical ship might deploy 2 to 10 times as much chain as the depth of the water it's anchored in. That extra length is intentional and essential. As wind and current push on the ship, that long chain acts like a shock absorber, stretching and moving with the pressure rather than fighting it directly. The weight of the chain itself creates enormous horizontal force on the anchor, not from above, but from the side. This lateral pressure is what drives the anchor flukes deep into the seafloor. The flukes, those curved arms on the anchor, bite into sand, mud, or clay, creating mechanical resistance. They don't just rest on top, they burrow in, sometimes penetrating several feet below the surface. The seabed itself becomes part of the system. Mud acts almost like glue, creating suction that holds the anchor in place. Sand offers friction and resistance. Even hard clay or rocky bottoms provide geometric locking. The anchor's shape simply cannot be pulled free without dragging tons of material with it. It's physics working in harmony with the environment. This is why anchor design matters so much. Modern anchors, like the Bruce or Danforth anchor, have evolved from simple hooks. Their curved shovel-like flukes are optimized to dig efficiently, while their design allows them to reset themselves if they start to slip. The geometry was developed through centuries of maritime experience and modern engineering calculation. So the next time you see a ship peacefully anchored in a harbor or offshore, know that it's not held in place by brute force. It's held there by an elegant dance of mathematics, physics, and seafloor mechanics, where a relatively small piece of metal can command the stability of a floating city. The anchor isn't strong because it's heavy. It's powerful because it understands how to work with the ocean, the chain, and the earth beneath the waves.